Okay, so this is the last lecture, and today we're going to talk about univalence. But it's going to take us a little bit of time to get there. So let me start with some observations about path spaces. Okay, so we've seen that path spaces play an important role in the study of the structure of spaces in general, and so, I mean, a lot revolves around them. So it's very natural to ask the following question given some type A. So we have a type A, and then we have some points in it. It's fair game to ask, what does the path space X of paths from X to Y look like in some specific case? You know, in general, you can't say anything, but it's a fair question. So, for instance, we could try something very basic. For instance, if I just take the simplest case I can think of, that would be that I have X and Y in the unit type, and I would like to know what is the path space from X to Y like? What does this look like? Huh? So what would you expect? Well, how many paths are there going to be in the space which has a single point? Well, presumably there won't be very many. There should be just the constant path on that point, nothing else. So you would expect that if you take here any points x, y, that then this space here is going to be. So how do I now say that this space always has exactly one path? Well, we learned that we should use equivalences when we can. So we should say this space is equivalent to the one-point space. That will describe the space completely. So that would be an example of figuring out what the path space looks like in a very trivial case. By the way, it's interesting to think about how we're going to pull this off. So what does this mean? What do we need to do? Okay, so we need to do for every given x and y, I want an equivalence. So to get an equivalence, if you're looking for an equivalence between two specific types, then usually what you just do is you give maps in both directions, f and g, and then you show that they are inverses of each other. Okay, that doesn't give you an equivalence, that gives you an isomorphism, but every isomorphism can be turned into an equivalence. There was a map, always remember there is a map from isomorphisms to equivalences. So if you have an isomorphism, you can fix it so that it becomes an equivalence. So what we look for to prove something like this, we would need a map. So what kind of maps would we need? Okay, so first we would need, so we're going to construct a map F which takes an arbitrary x and y in 1 and a path from x to y. Right? Oops, I don't need this. And it gives you a point in 1. And then we want another map like that, but this one goes in the other direction. Yeah? And then we are going to verify that they're inverses of each other. Now here, you can make a mistake when you try to define this by going too early for induction on x and y. You would say, I'm trying to do something for all points in the singleton space. So it's enough to do it for the single point, the star. Remember, star was the only element of 1. And you say, I just need to consider the case when x is a star and y is the star, and then it's all easy. But it turns out you really shouldn't be doing it like that. So you should postpone this induction business for as long as you can. So what we would define is f, x, y. So f takes an x and a y and the path p. So it takes the path p here. And now it has to give you an element of 1. Now, well, this one is easy. We're just going to return the star. Okay, how about g? So g takes x and y and an element u, so p lives here, u lives here, u, and now it has to give you a path from x to y. Okay, so this needs to be a path from x to y. Where do we get it? Here we use induction on x, y, u. Here we do use induction on because it's now you know, I say like how am I going to get this? How am I going to get the a path from these 2 points? So you say use induction on x and y. So it's a double induction. First you do it on x, and then you also do it on y. So what does that mean? Well, what is the induction principle for 1? It says if you're trying to do something for all points in 1, it's enough to do it for the star. So just need to define g applied to star and u. And then you say, well, that's just going to be, that needs to be, so what does that need to be? Now it needs to be a path from star to star, and that's a lot easier. You just define this to be equal to REFL on star. And so now you would have to verify that these two are inverses of each other. So verify. So first we need to verify what is f of, so let's see, okay, so let's see, f of, f at x, y, g at x, y of u is, what is this? So we would like to know whether this is equal to u for all x, y, u in 1. And so, yeah, just use induction on, well, in this case, you can use the induction on u. Okay, so induction on u. Say again? Yeah, use induction on u to verify that f, x, y, g, x, y star, okay? Well, what is this? G, x, y star up here. Well, now we want to show that this is star, so now also induction on x and y. So now we turn x and y into stars. See, I'm doing a very detailed thing here. F stars star. I do hope my x's and stars look sufficiently different. G star star star. Oh, okay. So what is this? G star 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 is actually I could have. Well, actually I was done here. I don't need the other induction. I'm sorry, because this one already computes. Okay. So you say, can I do anything here? Well, yes. F of x, y, p is star. So by definition, this is just star. And I'm done. So this is by definition of f. Okay. And then we need to also verify the second one. Let's see, how would that go? So g, x, y, f, x, y, p. Okay. Is this equal to p for all x, y in 1 and p from x to y? That's the other inverse. What do we do? Path induction, because p is unrestricted. See, this is why it was important to keep these points general enough so that when I get to this point where I have to show that I'll get the same path when I go around, that this path is unrestricted in its endpoints. So now I can say, okay, path induction on P, which means I plug in, for X I plug in Z, for Y I plug in Z, and for P I plug in REFL Z. What will I get? I'll get G, Z, Z, F, Z, Z, REFL Z. What is that? Okay, we look at here, up here, what do we know? F, Z, Z, okay, so which one are we going to use? So is this one here, G star star will give me REFL. Okay, so I say induction on Z, I can further specialize this to star, and now I'm going to have G star star F star star. Raffle star, okay, what is this? G star star, G star star, whatever is raffle. So this one here becomes, by definition of G, this is raffle star, and that's what I need because I need it to be equal to raffle Z. So, which is okay because this is, so I'm trying to show that this is raffle of Z. And yep, it's equal when Z is star. Okay, so it's a bit of a silly exercise. I just wanted to show you this because if I just gave you this as an exercise, you would very likely proceed slightly differently here, and you would say, "Oh, we're just going to do this for star." Okay? You say, "I'm showing something for all points in 1. It's enough to show it for x is star, y is star." So you would end up proving star equal that the loop space of star is the unit type. But then you'd be stuck because now you have a loop, but you can't use path induction on loops. You need to keep points. You need to keep paths free. So anyway, if you want to think about this, forget about this. When you wake up in the morning, say, "How do I prove this?" and try to prove it by induction on x and y immediately. So try to prove star equals star is equivalent to 1, and you'll see how it gets stuck. Okay, so what are some other examples where we want to know about the path space? So another example would be, for instance, if we ask about the path space in a product type. So suppose you have 2 points, say S and T are 2 points in A cross B. So I have 2 points S and T. And I'd like to understand what is the space of paths like from S to T. If I have a path like that. And what one suspects is that if you go across like that, it should somehow be helpful to go. You see, if I have a path here, I can map it to a path on the first component and the second component to get 2 paths. And if I have a path in the first component and the second component, I can get this P by going whoop, whoop, like vertically and then horizontally. So one, for instance, would expect that you should have something like this, that for all S and T in a product. So now we want to say, what can you say about the space of paths from S to T? And so here's a reasonable guess. A reasonable guess would be that this space must be equivalent to the space of paths from the first projection of S to first projection of T crossed the first projection this cross the second projection of S and the second projection of T. Yes. And so I'm not going to do this one, but what, again, you would proceed by exactly the same device. You would say, okay, so first you could attempt to use induction on A cross B. What is induction on A cross B? So induction always says, do it for the canonical element. So you would say, but S and T must be pairs, and then you would do it for pairs. But I think it's better to just try to write down these maps. So if I give you a path here, suppose P is a path from S to T, so it's down here. How do I get a path here? Well, this would probably map to a pair where this is more or less, well, you can just map P1, you can just map it, right? Every map, if I have a function from A cross B to A, then I can just map it, the path, okay? And this one would probably be P2P. But then for the other direction, here I'll have a path alpha, and here I have path beta. It's more interesting what to do here. You need to do something. But the idea is you move around like that, right? You have alpha here, you have beta here. Now you take this alpha up here so that it goes like this, and then you take beta, and they go boop, boop. So something should be there should be something doable here, and then you know, some calculations ensue. And you can go down all of these ways of constructing types. So maybe I can recall some other ones. So here's another one, and I hope this is going to ring a bell.
So
yes?
Examples were using the class basis are sets.
Nope, I don't think so.
Because now we actually show that this map is isomorphic.
Ah, okay, yeah, so that's what I was okay, so that I was pointing out earlier, so let me write it down explicitly. Recall, okay, if, recall, okay, there is a map which goes from isomorphisms from X to Y to equivalences from X to Y, okay, so if you just need any equivalence from X to Y, okay, E, then it is enough to construct an isomorphism. So to construct some I from X to Y, let's give this map a name. So I'll use, I don't know, randomly use epsilon here, okay? Because then my E can be taken to be epsilon of I. Well, that's not an epsilon. Epsilon of I. That was my point earlier, that if you're just looking for a specific equivalence, like you just want an equivalence, okay? So, okay, you can maybe have some fancy way of getting an equivalence by defining a map from X to Y, and then you show that all its fibers are contractible. That's one way. But a far more common way of getting an equivalence, in cases where you have something specific to work with like that, is to instead find an isomorphism. It's usually easier, okay? And then you know that every isomorphism can be turned into an equivalence. The point is that this map epsilon itself is not necessarily an equivalence. In many cases, it isn't an equivalence. But you don't care about that. I'm not trying to analyze the entire space of equivalences. I just need an element. So I just find an element here, map it over there, now I have an element there. It's just less work, that's what it is. Now, when would this not work? It wouldn't work when you want to control quite precisely which equivalence you will get. So there are situations where you need to be very careful about which particular equivalence did I get. If you use this epsilon trick here, then you might get a mess. You will get the proof that it's an equivalence will be nasty. And if you care about which one you got, then you shouldn't do this. But here we don't. Here, once we have an equivalence, we say we're done. So we don't care. So we do it this way. Okay, so did that answer your question? Okay, so here's an example. What can be said? What can you say about the path space? So if I have F and G, two maps from A to B, what can we say about F? Space of paths from F to G. When are two maps equal? Can we characterize that? And so we already, so what is this going? This is about function extensionality, right? So for instance here, what is this like? Recall we already spoke about function extensionality, which allowed us to say something about it. But if we want to be very specific and know what this thing is, then what we would do is we would show instead, so you would want to show that f A to B G, that this space is equivalent via a specific equivalence, by a specific map that we would also apply, not just any equivalence, although I think it turns out it doesn't matter which one it is. So that that this should be the same as this space. Okay, so that's what we would show. And more specifically, what one does is you define a certain map and show that that particular map is an equivalence. You can look at the hot book on function extensionality to figure out, because that's more useful if you know a specific equivalence which computes nicely and has its exact properties. That's the one you would want to use. It's easier than just saying, well, there's some equivalence and I don't know anything about it.
Last FY.
Yeah, of course. Yes, thank you. This one should be G of X. So it's a way of saying, I know what this space is like, the space of paths. It's actually a product of path spaces. It's a huge product of path spaces. Okay. And you can go on like that. Here's another one, which is maybe not as specific. Sometimes you don't actually compute it, but you have this. Say that a type A has decidable equality. Has decidable equality. When we have for all x, y in A, x equals y, or it doesn't matter whether you put or here or not, I think, because they're disjoint anyway, so or not x equals y. And recall that not x is by definition x arrow empty. So that's what a decidable equality means. You can decide, given any x and y, what you're going to get is, so an element of this space is a function. It takes x and y, and then it gives you one of these two options. So if it gives you the left option, then it will give you the left option with a particular map from x to y. If it gives you the right option, then it gives you a map which shows that there can be no path. Okay, and so then we have, for instance, a theorem like this, which is very useful, which tells you something. So this is called Hedberg's theorem. Not Hegbert's, oh, now I'm confused. I need to verify. Hedberg. Yeah, okay. I think I spoke to Egbert too much, and now this G is coming up. If A has decidable equality, then A is a set. Why is this about path spaces? Because to say that something is a set means that all the path spaces are propositions. So all the path spaces have at most one point. The proof of this is in the hot book, for instance, and this would be. Let's think for a moment. Let's just think topologically here. To say that A has decidable equality looks a lot like saying that singletons are discrete. Yeah? Slightly more constructively. So it's some sort of a discrete. Okay, I'm going to say nonsense, which then some of you will appreciate. It's a discrete Hausdorff space. Okay? Because you're thinking, like, why is he saying Hausdorff? So it's a discrete Hausdorff space, and so this is saying discrete Hausdorff spaces, we understand what their path spaces are like. They're boring. Take any 2 points. In fact, it's going to turn out that you take any 2 points and you can decide whether the path space is going to be either the unit or it's going to be empty. Right? That's what this is. But that's what will happen. Okay, so And another important example of understanding a path space is a loop space, right? A loop space is a path space. So you may well be interested in studying loops from A to A. And then that's also one way of understanding this. Okay, so this brings us then to the question of what about the path spaces in a universe? So what do paths between types in a universe look like? So given A and B, which are two types in a universe, we want to know what is A equal B like. Historically, type theory didn't really have it didn't fix the answer. So in general, when you have some sort of a theory, you may wish to fix the answer to certain questions, but not to the others. For example, if you're doing set theory, you're going to be very interested to know whether there is an infinite set, and you probably want to, like if you want to do it, you feel that if you want to do anything useful in set theory and use the set theory as a foundation, it's probably a good idea to throw in an axiom which answers the question as to whether there is an infinite set. And so most set theories do that. Some actually throw in the axiom saying that there isn't an infinite set, but then they reduce to something very easy. The interesting ones say there is an infinite set. So sometimes you want to give an answer to a question, you want to fix this thing you're studying, you don't want to keep it floating. But in other cases, maybe you don't. So, for instance, you're studying groups and you're wondering, well, is multiplication commutative? That's a reasonable question about groups. And now, depending on what you want to do, you may want to say, yeah, I want multiplication to be commutative. Maybe you have good reasons for that, and then you're going to throw that in, and from that point on, you're doing a billion groups. Or maybe you say, no, I want to leave this open. I want to say neither commutative, neither non-commutative. I just want to work in general. So here we are facing a similar situation where we're saying, well, what about the path space from A to B? What does it look like? For instance, when we had a similar question about functions, and we wanted to say, what does the space of equalities, space of paths between two functions look like? It turns out you can't really say anything about it, but we wanted to have an answer that would allow us to work with these things as we are used to. So we're used to working with functions in a certain way, and among other things, we want this to be the case. We want it to be the case that if two functions agree on their values, then they're equal. So we threw in function extensionality. We adopted function extensionality as an extra principle, because that's our idea of what is a function sort of comes with that. As a mathematician, you would say, well, function, it only matters what values it's returning. It doesn't matter how I defined it or how long it's taking to calculate its result or anything like that. I ignore all of that. I only want to observe the values that it's returning. So this is why we put it in. So now we're facing a similar situation. So we could either say, well, we don't want to know anything about the equality of the universe, we're just going to work generally. It turns out then there's very little you can do. And so it's better to have some sort of an answer. And more than one answer is possible here. So you could try various things, but let's think about practice. In practice, when are two structures, like when do mathematicians say that two structures are equal? Like two types, two spaces. When do they say that two spaces are equal? Well, they distinguish. So first of all, you put them against the wall and you say, what is your formal definition? If you point a gun in their head, okay? Then they're going to say, oh, no, set theory. And then they will say, two spaces are equal if they have the same element. Let's just take two sets. Two sets are equal if they have the same elements. And they will say, but, very often I want to consider isomorphic structures. We've already learned that trick. So equivalent structures. So they often say, I want to really consider isomorphic structures. And then they say, okay, but promise to be careful. So when you mean equal, you say equal. When you mean isomorphic, you say isomorphic. And they're just like, yeah, I promise, you take your gun away. And they wander off, okay? But then you go and you look what they do. They don't hold their promise because they will easily say, yeah, but you know, the integers is a subset of the reals and these other integers here, that's the same thing, right? We can just mix them freely. And so then they might say things, they might say silly things that don't make sense, right? They might say that 4 is an element of the real numbers. But no, but it isn't, right? 4 is probably an element of the natural numbers, but it's not, if you want it to be an element of the real numbers, then that doesn't work. So they get, from the point of view of formalism, they get sloppy because they start confusing isomorphism or equivalence on one side and equality on the other. Okay. But as anybody who's ever done mathematics knows, this is really, really, really useful, and we're not going to give it up. We're just going to say, like, if somebody forces us to say that equality and isomorphism are different, then we're going to say, yeah. But then when they go away, we're going to say, we're just continue doing this thing we're doing here because it's so cool. Okay. Now, this is not very mathematical. What we really want is, we want to fix the situation. You know, it's not an acceptable situation. You really want, if something is so useful that you really want it, then you should try to fix it. But it's not so easy. For instance, suppose we just keep doing set theory, and then we say, okay, let us pretend that equal things, the isomorphic sets are equal. That is going to give you a very strange kind of set theory, because what will you be doing? So you cannot just admit that isomorphic things are equal, because they're not. These two sets, 1, 2, 3, 4, are isomorphic. So if you say they're equal, if you say these two are equal, actually I can do this better. Okay, so here we go. We can say Yaka, the singleton Yaka, and the singleton Pope. Okay, these two sets are isomorphic. So if they're equal, then it'll follow that Yaka is the Pope. Yeah. So you can't do that. Or if you want something slightly more mathematical, you just prove that 0 equals 1. And then it still follows that Yaka is the Pope. Anyway, you get into trouble. So you can't do it in this straightforward way. So the question is, how can you do it? Is there a way to do it? And the answer is, you can do it, but there is a price to pay. You need proof-relevant mathematics. Why is that? If you're going to claim that isomorphic things are equal, because isomorphic things can be isomorphic in many ways, it follows that things will be equal in many ways. But for things to be equal in many ways, that means you brought in proof-relevant mathematics. So the price you pay is that you have to start paying attention to proofs as a mathematician. So far, you could have ignored proofs, right? Well, not entirely. I mean, you didn't ignore them on this level of activity of mathematics, but you could ignore them as mathematical objects. You make them, then you just forget about them. But now we won't be able to do that. So the idea is, just like before, we have an idea of what we would like. We would like to say equivalent types are equal. That's the driving idea. That's a dream. That's something that ought to be very, very, very interesting, because it's a piece of mathematics that is present everywhere in mathematics, in the practice of mathematics, in the actual practice of mathematics, it's present. But it's not present in formal mathematics. So it's a discrepancy between practice and what actually happens. People try to say, I said this many years ago to, who was it? Thomas Streicher. I was doing some sort of internal arguments in toposes, and I said, we're just going to pretend that isomorphic objects are equal. And then he said, yeah, but how do you know that's okay? And I said, well, it just means that I need to put in isomorphisms in the correct places. Because that's certainly the feel you get. Whenever you are switching from one object to the isomorphic one, it just feels like, yeah, if I'm really careful, I can just insert the correct kind of isomorphism. Yes? And he was sort of doubtful and said, well, I'm not so sure, not so sure. Okay, so he knew what he was saying and I didn't. It's not that trivial. If you try to really do it, you get stuck. If you try to do so, you can do it in certain cases. I mean, there are meta theorems saying, yeah, it's doable. But if you really want to do it full scale, it gets really complicated. So, how do we do this? We do it like this. We say, well, we're not going to say it like that. What we really would want to have, we want an equivalence from where to where? Well, between the identity type, so the path space, and the space of equivalences. We would like an equivalence. So now let me pick a direction because it's one of them is going to be, so we would like the equivalence of these two. Okay, and this is sort of a slightly inexact version of what the axiom of univalence is saying. It's saying the path space between two types is equivalent to the space of equivalences between two types, or the slogan is equality is equivalent to equivalence. And just to convince you that things can go wrong, if you try equality is equal to equivalence, you get into trouble. And if you try to say equality is isomorphic to isomorphism, you get into trouble as well. So isomorphism really is the wrong thing to say. You really need to use equivalence. It's not that easy. It's tricky. Okay. So this is Vladimir Voevodsky's Univalence Axiom. But let us be precise how we say it. We don't want to just say that there is some equivalence. We want to be specific about which one. So recall that we had the following. So there is a particular one which goes from the identity type. It's usually written like this: it to eq, something like that. It's a particular map which goes from here to here. So let's be quite exact here. So pi a b in U, A to B goes to A is equivalent to B. So there is a particular map like that, which we already considered. So how does it work? So it takes, okay, so we usually omit these arguments here. So take some path P in the universe. Okay. Actually, I should ask you this. How do you do this? How do we define this? We're trying to do something for an arbitrary path with loose endpoints. So a little ring goes bing, bing, path induction. Yeah, because you have arbitrary endpoints for arbitrary, so take arbitrary endpoints A and B and the path P from A to B, and then you want to do something. So that just says that we are trying to use path induction. So we do path induction. So the path induction says all you really need to provide to get this map is for every C in U, you need to give me, so here we're going to plug in the reflexivity, but this doesn't depend on the reflexivity, so you won't see, give me an equivalence here, like that. That's what path induction says. It reduces it to this. But that I can do, okay? Because I just say, well, okay, C maps to the identity equivalence on C. So the identity equivalence on C. So now I have a map. So there is a map which turns paths into equivalences. This is sort of complicated, but what you need to remember is just this. Given a path P in the universe, we get an equivalence id to ec P between A and B. And what we know is that this id to ec, when you give it the identity equivalence, it will give, when you give it the reflexivity path, it will give you the identity equivalence by construction. And so now the axiom of univalence, so actually univalence axiom, abbreviated usually as UA, says is equiv id to be quite precise, because we're making such a big fuss out of this, so for all A, B in U is equiv id to ec for this given A and B. So here I would need to say, you know, id to ec, it really needs to be subscripted here with A and B if we're quite precise. So we're saying this map is an equivalence for all A and B. So for all A and B, this map is an equivalence. This one here. That's what the univalence axiom says. Now there is a sort of this. There is a lot packed here, because if you start unpacking this, it's saying, okay, so this is saying that for every A and B, every fiber, every homotopy fiber of this map is contractible by definition of what it means to be an equivalence. And so actually there is the sort of what you get out is the sort of the useful form. Okay, it amounts to a couple of things. The first one is that you, okay, so first of all, we do get a map. So because this is an equivalence, because this map, so there is a map called id to ec AB, which goes from left to right. Because it's an equivalence, it has an inverse. So there is an inverse, that's the first thing. There is a map, and this map is usually called little UA, okay, which goes from equivalences and turns them into paths. And this is a super useful path. This is a super useful way of making paths. This will allow us to make lots of paths. You find an equivalence, you get a path. Just like quickly, can you think of an interesting equivalence from integers to integers? Sure, add one, like successor, okay? Successor is an equivalence because it has a nice inverse, the predecessor and so on. So there is going, in the universe, now there is going to be a path from integers to integers, which is non-trivial because it ought to act like a successor. So there is a map like that. And then, of course, there is the inverse, okay? Let me just collect these things here. There is a map id to ec if we're super careful, you need to put these subscripts here, but I'll eventually drop the subscripts. So there's one going like that. Okay, and now they are inverses of each other, so that says something. And then not only are they inverses, they form an equivalence. So you want to pull something useful out of that. But I see that do I want to explain this now or after the break? Let me think. Well, let's do it now. So there's going to be, okay, so first of all, we're going to have the inverses. So what do the inverses say? So it says, if you take a path P and you turn it into an equivalence, and then you use univalence to turn it back into the path, you will get a path. Okay. So where is this happening? This is happening in A equal UB. That's one. And the other one is, if you take an equivalence E and you turn it into a path, and then you turn it back to an equivalence, then you're going to get, and now this is happening here, E back. There's another one, which is sort of what you could call the point that you get. So it's this. What happens? So I can do the following. Let me. So this is the one that's going to take 2 minutes, but let me do this. Okay, I can do this. I can take an equivalence from A to B, like that, and then I turn it into a path. Here's my huge universe. And then I have A, and I have B, and because I have an equivalence, there is a path here called UA of E. That's the one that is given to me by the univalence. Okay, now over here is A as a type. Here is A as a point of the universe. Here is A as a type. Here is B as a point of the universe. Here is B as a type. Now, if E is an equivalence, it's really like a map going here this way. Okay, so E is a map going this way. So I could ask, so there are two things I could do. I take a point here, X, and I can map it over with E of X. Because E is an equivalence, so it's a map. It goes from A to B. But I could also do something else. I could take this X and transport it along this path over there. So I could get here another point, which would be transport X along UAE. And so it's a natural thing to ask, how are these two related? So the computation rule says, okay, if you transport in some vibration, in some vibration, so I'm going to write down this vibration and then you'll wonder what it is. So it's lambda x u x, sorry. And you transport along UA of E, this x, then you will get E of x. And this is happening in B. So this one is very useful. This one actually lets you compute things, because of course, what is the whole interest in this? The whole interest in this is that I'm doing something inside A. I know that A is equal to B. I would like to do the corresponding thing in B. I just transport, because that's the point of transport. You have a path here, therefore you can transport. But when I transport, I want to know what I got, because I'm transporting over a specific path, namely one of the form UAE. I want to know what happens. Well, the thing that happens is you're just going to get E of x. So this is sort of the content of the univalence axiom. When you unpack it, will give you these things. It will give you an inverse that turns equivalences to paths, so UA. So you get these inverses, but this is also quite important. So now I think we're ready to have a break. Okay. So maybe let's go for like, I don't know, most 10 minutes, so we can try to finish today. Okay, that was the univalence axiom, and in order to understand how to work with it, we should just look at some examples. But what we should expect is that it allows us to calculate the identity type between two types, so the paths between types. And moreover, we know what they will look like. They will be equivalent to equivalences. So we really have this possibility to say, yeah, equivalent things are equal. Where are equal doesn't mean you just pretend they're equal. It means there is a way of transforming an equivalence to a path. And then you can use that path in transports and everywhere to achieve whatever you want. And this is necessary because we know that there will be spaces whose space of equivalences is quite interesting and it has rich structure. So if we say that equality is equivalence, so again, this site can have rich structure, therefore we have to allow this site to have rich structure, so this site cannot be just ordinary logic where things are just true and false. It has to be something more complicated. Let me also make the following comment. In general, we can define the following. A dependent phi. So suppose we have a dependent type B from A to U, like this. We say that this is is univalent when, see this picture here, nothing requires, in this picture, it doesn't matter that we have a particular fibration. So this is the fibration, so this is the type family which takes every A as an element of the universe to itself. That's why it's written here as lambda x ux, because it takes A, gives you A, it takes B, gives you B. This could be any fibration. So let's draw the picture for any fibration and see what it gives us. So we could say, no, well, we have some base space A, and then you have 2 points x and y, and up here I have B of x and B of y. So I may consider, on one hand, I may consider paths from x to y, but on the other hand, I can consider equivalences from bx to by. Yes? So I can think of ways of getting from one fiber to the other. How can I get from this fiber to that fiber? Well, I can get from this fiber to that fiber by transport if I know of a path down here. But I can also get from this fiber to that fiber by some map, and in particular, an equivalence, because transporting along a path actually gives you an equivalence. So I should say, so maybe in some cases, the equivalences between the fibers are like the paths between the fibers. So when the following happens, for all x, y in A, if I look at the paths downstairs, that space can be compared to the equivalences between the fibers. So we say that a type family or a family of spaces is univalent when this happens here. So what does this say again? It says paths between things in the paths in the base are like equivalences over. This is going to have uses in both directions. For instance, suppose I want to know what the path spaces in A look like. So I'm interested, I want to say, I want to know what this is like. Well, if I can guess a B such that this, for some reason I know that this is univalent, and I can calculate these things, then I learn something. But my point is, univalence applies, the notion applies to also just general things. For instance, you could say, let's try an example, okay? So for instance, when is B, which goes from the unit type to U, univalent? Well, so I just have a single point here. So this is like having a type. Okay, so this is what a univalent type would be, because it's just one point in the universe. Well, okay, for all x, y in 1, x equals 1, y needs to be the same thing as bx equivalent to by. But when is this inhabited? This is inhabited by induction on 1. This is the same as saying star equals 1 star needs to be equivalent to B of star is equivalent to B of star. But this is 1, as we calculated earlier. B of star equals B of star. What does this say? Well, this is saying that there is just a single equivalence from B star to B star. There is a single auto equivalence. So what would you call a space that has just a single equivalence? Well, I don't mean, see, obviously I don't mean there is exactly one equivalence. What I mean is the space of equivalences is contractible, of course, because there will be lots of homotopic versions of the identity map and they will all be an equivalence. So what kind of a space is this? So it's something like a rigid space or something, right? It's something that has no symmetries whatsoever. It doesn't have any self-symmetries. You could also think about what happens if you go from 2 to u. If you go from 2 to u, you also get something. Okay, but I'm not going to go into that. I would like to do something else. But this is also worth thinking about because in order to get a grip on univalence, it maybe is useful to also think about these related concept, the more general concept. So if we plug in this, you say the identity from u to u to get the ordinary, to get UA. Right? What I'm saying is this here generalizes this picture here, because you just take A to be U and you take B to be the identity, and then you'll get the other one. Okay. So let's see if half an hour is enough to do something interesting. Okay, so let's try to do this. Okay, so first let's recall what the components here are. Okay, so first of all we had the circle S1, which had a base point, and it had a loop from base to the base. And it had an induction principle, which I will use constantly, so I'll remind you of it whenever I get to it. And then we have, well, we didn't actually ever have z for integers. But what I mean here is z, what I really mean to say is z plus 0 as an abelian group. Well, it's not just any group. Which group is it? It's the free group on one generator or something. There are many ways to say it, but so we want this to be the additive group of integers. It's not terribly interesting to see how this gets defined, because it's going to be exactly like the usual constructions of the integers, if you've ever seen any. So either you start with the natural numbers and you complete to integers by subtraction. So then it would be some sort of a quotient, so a high reductive type. Or you could just say the integers are 0, the positive integers and the negative integers, and then the positive and the negative integers are like natural numbers, and you could sort of put the integers together like that. It's slightly more pedestrian, but would also likely be more convenient in some cases for formalization. So there are lots of ways of doing things with integers. We are familiar with integers, so I'm just going to not dwell on this. You get what you think you get. Okay? And it's going to have decidable equality. It's a set. It's not mysterious. Then what is this Π₁ business here? Okay, so there are two things here that we really would want to claim is, so let's do the Π₁, so the fundamental group. So recall, first of all, if I have a type X, or let's say A, if I have a type A, and I have A in A, then I have the loop space at A, which was this thing here. And that's just loops at A. As I already remarked several times, I think the loop space can be a fairly complicated space. It can carry a lot of higher homotopy structure, so, but it kind of looks like a group, because if I have a loop, well, there is the constant loop. If I have a loop, I can go in the other direction to get the inverse loop, and I can compose loops. So it's beginning to look like a group, but it isn't a group because of the higher homotopy structure. You need to cut it down. Classically, you cut it down by taking a quotient by homotopy, or if you are more inventive, you would take the path connectedness components inside this space, and the components would be the elements of the group. It doesn't really matter, I just said the same thing again. You take the quotient. So you need to quotient, and we discussed this. So what you need to do, you force it to be a set. So this you define to be the zero truncation of the loop space. And then you need to show that you get a group, but you do get a group. Okay, so in our case, and then if we have some particular A in mind, then we don't necessarily write it this way all the time. So in particular, so now what we're going to do is we are going to show that the loop space of the circle, well, based at the base, yes, is the same thing as the set of integers. Okay, so it follows that Π₁S², okay, I'll write base everywhere this time, is the same thing as omega S1b, which is the truncation, the set truncation of, it's the set truncation of Z, but Z already is a set, so when you do that, you don't get anything, you just get Z. Okay, so I'll show the stronger thing, that namely for the loop space, you don't actually have to quotient it, you don't have to do this thing to it. Why is that? Well, that's because the componentness, the connectedness, the components for the connectedness here are boring. They don't have any interesting topology, so you don't have to do that. They're contractible. Okay, so by univalence, so enough to show, this is not really the application of an application of univalence yet, not a real one, that this is equivalent to Z. Because equivalent things are equal. So, how do we do that? So I always say, you know, you first have to try the brute force and ignorance approach, otherwise you will never appreciate what goes wrong. So what is this? Well, this thing here is just the loop space of the base. And this is supposed to be the same thing as Z. Well, equivalent at least. Okay, so how do you find an equivalence? You find maps going both ways. So we want to have a map, say F, which goes to, let's see, which way do I have it here? I want the easy one first. Okay, so I say, okay, Z needs to go here. And then I want G, which goes backwards, and I want them to be inverses of each other. And so you can do this, and you can start defining your loops. So let's try to define a candidate for F. Okay, so you say, okay, what is F of K going to be? But this is, you know, It's not that surprising because here's my circle, right? It has its loop. And now I have an integer. What could I possibly do? Well, I need to run around k times, right? That's what you expect is going to happen. You map an integer to the path which loops around k times. And if k is negative, you just go in the other direction. So this can be defined by some sort of induction on the integers. And so more or less you get this. It's going to be loop, composed with itself k times. If k is greater than 0, and it's going to be raffle b if k is equal to 0, and it's going to be loop composed with itself minus k times if k is less than 0. And you do this because you can do this by cases, because for the integers you actually know that every integer is either greater than 0, equal to 0, less than 0. And then this one you need to do with a further induction on the natural numbers and so on, and it's all very finicky. But anyway, we're just going to write this as loop to the k. Okay?
Like reverse loops?
Yeah, sorry, thank you. This one needs to be loop to the -1 everywhere. Like that. Thank you.
Then we'll take them k times
Minus k times? No, minus k times if k is negative. Yeah, if k is -3, then you compose loop to the -1 3 times, which is like composing loop -3 times. Geometrically, this part is clear geometrically. You do an induction like that, you can do it. Not a problem. Okay, how about the other one? The other one seems more interesting, right? How are you going to get an integer out of a loop? So, candidate for G. Well, how do you start? You say G of P equals, what is P? P is some loop. What do we want? We want the winding number. That's what it's called. We would like to assign to P, it's the thing that is called the winding number. And students, like you go to complex analysis, and then you say, let the winding number be the number of times that the loop goes around clockwise, and it's negative if it's counterclockwise, or the other way around, probably the other way around. And then everybody says, yeah, that's an obvious concept. Well, is it? So here, because we have a language that ties our hands behind our backs, I can't wave my hands to convince you that there is this number, so I need to do something. And so it's doable, but let me just tell you what is going to happen if you go down this road, and then we're not going to go down this road. What we're doing is we're going to get stuck, okay? And we're going to get stuck for a reason that is very similar to a reason we had before. At some point, we will want to prove that something holds for all loops. Okay, so here we don't know what it is. We want something like the winding number. What is that? Anyway, afterwards, we'll still need to verify the following thing. For every loop from base to the base, f of g of p equals p. And this is happening bb. So this is a homotopy. And we will be stuck trying to prove that something holds for every loop, because we can't use path induction for loops because both endpoints are fixed. We should not try to do this. What we need to do is we need to make at least one of these endpoints free. By the way, there is a version of path induction. You can use path, so this is something you should read in the hot book. You can use path induction if both endpoints are free, but you can also use path induction if just one of the points is free and the other one is fixed. It's also okay. So we need to, at least one of these endpoints needs to get unhinged. Otherwise, we will not be able to calculate anything because we won't have path induction. So That means now, instead of working just with loops, we need to do something slightly more general. So that's what we're going to do. Okay, so problem here. Cannot use path induction on P. Another way of understanding what is going on is that we're trying to do something at a single fiber. We are too obsessed with the base point. We need to really pay attention to the rest of the structure of the circle. We shouldn't be this obsessed. Okay, so let's try. So we're going to go like this. This is what I'm going to show you now was the first example of a technique called the code-encode method, which is a general technique for calculating calculating and generally working with calculating identity types, so path spaces. Okay, so we're going to define two things. We're going to define two families, code and decode. So these two maps, like that. Okay, as follows. I need these so that I can generalize the F and the G to the case where one of the loops is free. So first we define D. Okay, so D is D of X is B equals S1X. So now I unhinged one of the endpoints. That's my first step. I said I don't want loops. I'm going to let one of the endpoints go free. But now I will have to do everything for the case where this point here is general, is not B anymore. Okay, that one was easy. Define D. Define C. I don't know why I did it in this order. Okay, now this one, it will be by path induction. Let's see where we're going with this. Okay, the purpose of D is to let loose one of the endpoints. The purpose of C is to have this. When I plug in X, so I just turn this B, which is the base point, into a general X. But when I put in B again, I want this to be Z. So left-hand side, I let go of B here. This one becomes X. Right-hand side, I need to do something here. I need to generalize this one, but so that it depends on X. But when X is B, it needs to be Z. Well, that's path induction. So by path induction, because C says you need to do something for every point in S1. Yeah? Okay, so C of the base is Z. That's what path induction on the circle says. First, tell me where you map the base. Well, I map the base to Z. Okay, and then it says, okay, now you have to give me a loop. Yes? So also give a loop. You have to say, where does the loop go? So C needs to map the loop. I need to lift the loop. And it needs to map the loop where? Well, the loop needs to be above. So it goes from C of B to C of B. And it needs to be above the loop. And it needs to be with respect to what vibration? Well, C, obviously. Okay, so what is that? Okay, so C, lifting the loop, says C of B by definition is Z. So what I'm saying is I need a loop from Z. This is, yeah, I need a loop like this. I need, this is, This is not C, I'm very sorry. Okay, so we're going to think about what stands here. Let's just maybe recall, on the side, let's recall how path induction, circle induction works in the general. So circle induction in the general case is something about loops above loops. But what is the circle induction in the simple case? So the circle induction in the simple case says this. Suppose you want a map S1 to some other space X. What you need to do is, you need to map the base point to some point here, and then you need to lift the loop. So you map this to some point, I don't know, like X, and then you need to move the loop to some path P, which goes from X to X. Okay, so that's the simple case of path induction. The general path induction is the case where X depends on S1, but here it doesn't. You see, I have the universe all the time, so it's a simple family. So this business of dependent paths over paths goes away. It just becomes this. To define the map C from S1 to U by, sorry, I'm very sorry, you should correct me. This is circle induction, not path induction. Circle induction. Circle induction. You specify where to put the base of the circle. Okay, I'm saying the base of the circle will be the integers. And then you need to say, how do you intend to map the loop? Well, the loop needs to be mapped to a path from C of B to C of B, which is the same thing as a path from integers to integers in the universe. So now I need to say, okay, I need to move this map. But to have this, by univalence, I can do something interesting. I say, this thing here, by definition, is going to be UA of successor. So let's think about this. Why does this make any sense? Because, let's see, what do we have? Okay, so first of all, successor, which is just the map, k goes to k plus 1, is an equivalence. Because it has an inverse predecessor, and you can actually show that they form an equivalence. So SUK is something that is an equivalence from Z to Z. UA turns equivalences to paths. Now I really did use the univalence axiom. I said, I want this Z. See, what am I trying to do? I'm mapping the circle into the universe such that the base point maps to the integers, to the space of integers, and the loop maps to a certain path. But a path is like an equivalence. So I map to the successor. So now I have C, and I have D. So again, D is just the loops unhinged. So for every X, I consider the space of paths from B to X. And then C is the right-hand side. It's the other side. I know that at the base, it wants to be Z. But then I also need to produce a loop from Z to Z, and I use successor. Why do I use successor? I use successor because otherwise, because now I want to show that D of X is equivalent to C of X, it's not going to work out if I use here just Z everywhere. It's not going to work out. Okay, so now my plan is this. Plan.
Universal cover the circle.
Oh yeah, I was waiting for somebody to say that. And he's a very good student. Which one is the universal cover?
One called C.
Which one looks like the universal cover to you? I would say that C is more mysterious. First of all.
Well, C defines the deck transformations. That's what C does.
It does what?
It defines the deck transformations.
The deck transformations. There's a name for this thing?
Yes, so the group of, so if you have the universal cover, then the set of homeomorphisms over the base space, this is the group of the deck transformations.
Yeah.
Called deck transformations.
Yes?
So C just did the generator of the group of the deck transformations.
Okay, so the deck transformations, and is this one you would call the universal cover?
I suppose, yeah.
Right? Because this is saying the points above X are the paths from B to X in the circle. Isn't that how you get the universal cover in general? I mean, in general, that's how you do it. Yeah, you say what is the fiber above a point? You have a point in the base, you want the universal cover. What's above it? You say, well, it's the space in some shape or form. You say it's the space of paths from the base point to the other point. So this one is like the universal cover. Okay, and this one deck, as in D-E-C-K.
The shift cards.
Deck transformations. Okay, computer scientists, of course, knew about some of these things, but they renamed everything, so they call this decode-encode methods. Yeah. Okay, so now, what is our plan? Our plan is to show that for all x on the circle, C of x and D of x are equivalent. So C of x is equivalent to D of x. Let's work this out to see what it says. It says, oh, now it's backwards. I should have the C and D, the way I wrote things. This one is the D, and this one is the C. Okay, so what does this come to? This comes to for all x in S1, B S1x is equivalent to this C of x thing. I don't have a good way to write it because I defined it by induction, but that's what it is. Okay, and why would this be useful? Well, in particular, when we plug in for x the b, we get b S1b is equivalent. What is C of b? Is z, which is what we want. Yeah. But why did we make this move? We made this move because now here we have chances, because we have an arbitrary point on the circle and an arbitrary, and then this ought to be helpful in showing using circle induction to do things. So okay, can we carry out the plan? Yeah, well, let's do. So we need to find two maps going back and forth. So define. Okay. So first we need to define E, which will go from, this is the encode, that's why it's E, x from S1 D of x to C of x, okay? And then we're also going to go the other way around. So how do we do this one? What does this want us to do? This wants us to do the following. E at some arbitrary x takes a path P. So where is P from? This P is, it goes from B to X. Okay? And now this needs to be, okay, so point here, a path from the base to the point, and now I need something in here. Okay. Well, how could I do that? Let's think a little bit. Here's X, here's P. It's part of, think of it as part of the circle. It keeps going, but it came all the way to here. Above X, so there's the rest of the circle. Above x, I see the integers. I have the integers here. This is C at the base. But I really want something that is in C at the x, whatever the C at the x is, because it's a bit mysterious because I did it by circle induction, so I don't have a concrete grip on it. But there's something I do know, because there is a path from here to here. There is an equivalence from here to there. Because if I transport by P, right, I could take any point here. I need something in here. I could take any point here and transport it along, and then I'll get a point there. I could do that. So how about we take 0 and we transport it along P here. So this is going to be transport along C, take P and transport 0. So whatever corresponds to 0. Notice what will happen if I plug in for P the loop. If I say B is the base, X is the base, P is the loop, that means I will be transporting along the entire loop. But that, by the definition, will be like transporting along the univalence of successor, which will be like adding 1. So when I make the full circle, I will shift up by 1. That's my E. Then we need to define decode, which will go in the other direction. P x S1 C of x D of x. How do this one? Well, this one we do by circle induction. Why do we do it by circle induction? Because we're mapping out of something that was defined by circle induction. It's going to be easier to do it like that. Okay, by circle induction. So I need to do what? I need to define what D does with the base. So D of the base is, what does it need to go? It needs to go from C of B to D of B. What is this C of B business? This is Z. And what is this thing here? That's the loops. Okay. Oh, we had that one earlier. That was our F. It's this one here, right? We want to take an integer to a loop. That's what this is what is going on. Okay, so fine. D of B is defined to be lambda k in int loop to the k. Okay, but that we're not done yet. We also need to lift the path. Also need to lift the loop. That is to say, we need to find a path above the loop. Yeah? Okay, so I'm going to skip this one, and you can read about it in the hot book, because it's just very technical and doesn't really give you much, because it's a loop. It's about, it's the vibration. It's just not going to be illuminating at this point. Okay? I want you to follow the overall structure of the argument. You want to do it, you want to do this. You can't do this. You generalize one of these points so that you have b equals x. You need to generalize this. You cannot just keep this to be z. It has to vary with x appropriately. You define c. Now you say, we're going to show that these are all equivalent, because the equivalences I'm interested in is just a special case at one of the points. I have D, I have D, so what is left over? Verify. Well, verify what? So we need to verify what is D at x of E at x of P. We want to know that this is P. And then the other one as well. So what is going on? X is in the circle. P goes from the base to x, and now I want this. How I do this? And I need to do this for all x in S1 and all paths from B to x. One of the points is unhinged. I am allowed to use path induction on P. So I plug in the case when P is reflexivity on B. I get D of B, E of B, refl B. What is that? We look at the definitions, and we see that this equals D of B. E at the base is just transport. Transport in C, refl B0. That's what it is by definition. Okay, but transporting along reflexivity, transporting along the constant path doesn't do anything. So this is D of B of 0, which is loop to the 0, which is refl B, and we're done. Refl B, and we're done. Okay, let's verify the other one. What is E of x of D of x of some element little c needs to be equal to little c for all x in the circle and c element of c of x. This is a bit more mysterious because I don't have a good grip on this one, except when it's C of B, then it's integers. Otherwise, it's some equivalent version of integers somehow, mysteriously. Okay, what could I do? Now I use circle induction. Because I'm showing that something holds for all points in the circle. So let's just do so for the circle induction now I need to work a little bit. Let's just calculate what we get. Okay, so we are going to show, one of the things for the circle induction is that you need to show that it holds for the base. Whatever it is you're doing, it's holding for the base. That's what we're going to do. Then there is some business about paths, which again I'm going to skip. So circle induction, verify, first of all, verify for X is the base. Okay, so E of B of D of B of C equals C is what we would like to get. But now, where does this C come from? C comes from C of the base. But C of the base by definition, where are we? C of the base by definition is integers. So that's just integers. So we're dealing with an integers. So we want to do this, and we want to do this for all C. Okay, does this help? Yes, it does. What is D of B of C? By definition, so let's calculate. E of B of D of B of C is E of B. So D of B of C, that's loop to the C. Okay, by the definition of D up here. Where are you? There you go. D of B of C is loop to the C. Now, what is E of B? Well, we're lucky. E of B, we know what it's supposed to give us. It's the transport business. So it's the transport in C of this loop, K, of 0. But this is going to be, because we defined that C, again, we go look, what happens? C lifts the loop to the UA of successor. So we are really transporting along, so this is going to end up as being...
What is K here?
K is C. Oh, K is this little c, yeah, sorry. K is the little c. Like that. Okay, so this is going to, after you unfold the definition of C and how the transport works, but what we're, okay, so, well, we can actually draw a picture. Okay, so here is the base. Here is the loop going around C many times. In the base, over the base, here, I have the integers, and inside is 0. And now I take this 0, and I transport it along this loop, around k times. But the way things are defined is that as I transport once, I will get one instance of UA of successor. So this is going to be UA is going to be the successor applied k times to 0. C times. What can I just say that k equals C? Okay, so C times. Because now we have to go a little further back, because univalence, where is it, says if you're transporting something of the form UA of E, then you just do E of X. So, but we're transporting UA of successor repeated k times, so we're going to get successor repeated k times by general properties of how transport works. So how much is C plus 0? That's just going to be C, and we're done. And this was the first proof where something interesting happened, apart from loads and loads of interesting things that Vladimir Voevodsky had already done before that. But this was the first interesting case of an interesting case with a circle, with a higher inductive type. So that's how calculations work. This works in proof assistance, and that's it. And we didn't know how to do this by hand The first time this was done, it was done in a proof assistant because we didn't believe ourselves that we're doing it right.
I remember you walking around and asking this question: how to define a circle? We want to have a circle first, and then everything will be good.
Yeah. So since we're recording this for the rest of the internet, actually there is a little anecdote. So there was an Oberwolfach meeting in which we were we figured out what the circle is supposed to be, and we sort of knew, and then we knew sort of how the spheres would go similarly. And then at the very end there was an open problem session, and Steve Audi was writing open questions on the board. And then somebody said, what is a sphere? How do we define a sphere in type theory? And he's like, how do we define a sphere in type theory? And then Peter started jumping up and down, saying, I know the answer, I know the answer. And then Steve looks at him and he says, sit down, Peter. This is the open problems session. This is not the solutions session yet. That one's coming afterwards. Okay, that's it. We're going to talk about the exams offline, I think.